Digital information is consistently at risk of corruption. In order to minimize the loss of information, computer scientists and mathematicians use tools known as error correcting codes. These error correcting codes work by adding redundancy symbols to the original data, which are extra bits of data meant to help recover pieces of the original if it would ever be corrupted or damaged. Error correcting codes are used in many things that you use on a day-to-day basis, from QR codes to satellite communication to what we will be discussing in this video, CDs. If you've ever used a scratch CD that was still able to work perfectly, it is because of error correcting codes, and more specifically, a variation of Reed-Solomon coding, which allowed the destroyed data to be restored. Why should you care about this? While not as popular as they used to be, CDs are still used all the time and rely on the codes that we will discuss to protect their data. Furthermore, similar error correcting codes are used in many other ways to protect digital information. And in a world dependent on digital information, they are extremely important. For this video, we're going to assume that you have some knowledge of the following topics, and if you don't, we've linked some videos to help explain them in the description. So why Reed-Solomon codes? Well, for starters, one of the benefits of Reed-Solomon codes are that they can achieve optimal error correcting ability for any given amount of redundancy, which makes them very efficient and useful for devices like CDs. We know this because they meet what's known in coding theory as the singleton bound. The singleton bound states that for each nkd code, k is less than or equal to n minus d plus 1, or that d is less than or equal to n minus k plus 1. In coding theory, k refers to the length of a message or the amount of important information. N refers to the total amount of symbols, including redundancy, and D refers to the minimum distance, which in simple terms is how different two code words need to be to detect and correct errors. If you're confused, the singleton bound simply upper bounds the possible values for k and d. So for d, it states that d needs to be less than or equal to n minus k, which is just the number of redundancy symbols plus 1. Now we can prove that the singleton bound is true by doing the following. For starters, we want to prove that the number of valid code words m equals c, m being shorthand for c, satisfies m is less than or equal to q to the n minus d plus 1. Q represents the alphabet size, with the alphabet being all of the valid symbols for your code. For example, if you're writing data in terms of bytes, you would have 256 unique symbols, as you can represent 256 different values inside a byte. Therefore, your alphabet size, or Q, would be 256. Now to start, let C1 to Cm be the code words in M. Let's prefix Ci prime be the first n minus d plus 1 words for every I in M. If there exists an I not equal to j for which Ci prime is equal to Cj prime, that means that the code words agree in at least n minus d plus 1 locations. That means that the distance between Ci and Cj would be less than or equal to d minus 1, which contradicts the fact that the minimum distance of a code is d. This means that all C prime I must be distinct and that the length of k can be at most n minus d plus 1. This means that m is less than or equal to q to the n minus d plus 1, and that k is at most n minus d plus 1, which is the singleton bound. For Reed-Solomon codes, d equals n minus k plus 1, which means that it meets the singleton bound and is optimal.
For our solution, we'll be using a variation of Reed-Solomon code. For decoding our code word, we'll be using the Sugiyama algorithm. It is important to note that the method used for CD error correcting by computers is Gallows field, which we will not be discussing in this video. The rules are slightly different as you will use powers of twos, but the concept remains the same. For computers, Gallows field is easier to do computationally, but is a more difficult topic to understand. To start encoding, we need to create a polynomial with our encoded message. Let's look at some examples. Let's say we want to encode our message 1, 2, 1. Then our polynomial would be x squared plus 2x plus 1. Note that there's a 1 in front of x squared. Another example, 3, 4, 2, and 1. Our polynomial would be 3x cubed plus 4x squared plus 2x plus 1. To encode our message, we need to have some parity bits, or in other words, some way to determine our message has been corrupted. The easiest way to do this is to evaluate our functions when they equal to 0. Right now, our polynomials we are generating cannot detect any errors, so we need to extend them in order to do that. Here we have a generated polynomial, g of x. When we plug in either 1, 2, 4, or 8, our generated polynomial evaluates to 0. Here we also have a formula that will help us create a code word with parity checks. Note that n is the total size of the code word and k is the message size. In this example, n will be 7 and k will be 3. We first need to extend p of x by multiplying it by x to the 4th power, then dividing it by our generated polynomial. To create our message, we take the remainder and subtract it to our extended polynomial. Cut. Here's our completed computation of m of x. Now that we have m of x, we can now check if we have done this correctly by plugging in the values 1, 2, 4, and 8 to m of x. And we see that they evaluate to 0. Cut. Here's an example if our code word was corrupted. For example, a scratch on a CD. Note that 1, 2, 4, and 8 no longer evaluate to 0, which means our code word was corrupted.
Know our message is okay if when decoding, we input the numbers from the generator matrix, that being 1, 2, 4, and 8, into the response matrix, and they equal 0. If they do not equal 0, then we start error correction first by finding the syndrome polynomial. This message below was received with errors. First, though, finding out a new polynomial, the error polynomial. We denote this as e of x. The error polynomial we subtract from the received polynomial to receive the sent polynomial. As you can see here, we have all of the powers of x with 0 coefficients and then 2 with y's. These are correlated to the 2 errors that we can correct with this algorithm. We have a few declarations of equivalence here, which we will use in our syndrome polynomial later. And we will be using the roots of the generator matrix in these. Here is the syndrome polynomial, which we use the equivalencies from above to construct. We also have the syndrome polynomial here using the roots from above, or using the roots from the polynomial. And here we can organize it and sort the terms by error. Once we have the terms sorted by error, we can treat them as a geometric series and eliminate a lot of these terms. So we multiply by like terms on either side, and we eliminate a lot of the waste here until we get a nice and clean syndrome polynomial with like terms, or like terms sorted by error number. After this, we need to calculate the error locator polynomial, which we will be using the definition for now, which is just the two roots where the two roots being the x values where the error occurred. We multiply this locator polynomial by the syndrome polynomial to achieve the error magnitude polynomial, but we also use modular x to the fourth here to clean up some of the numbers. The error magnitude polynomial is denoted by the omega, and we first of all can rewrite this as syndrome times locator minus a function f of x to the times x to the fourth. And we need to multiply this by n, which on either side, which n will be the constant factor from the locator function, or the locator polynomial. Next, we'll be using the extended Euclidean algorithm. This algorithm is used for finding greatest common denominators, and for our purpose, we will save the b and r values and stop the long division once the remainder is a lower degree than the amount of errors that we can correct. We calculate syndrome divided by x to the fourth using this algorithm, and the remainder becomes our magnitude, and the b value becomes our locator. After decoding, we must divide by n, which we put on both sides prior to this, and then the magnitude becomes 1 for our example, and the locator becomes negative 16x plus 1. After this, we need to leverage the fact that our redundancy values from the generator are powers of 2 using the inverse of the locations, and given the degree of the message, we will find out where our errors are. We then go back to the definition of the error magnitude polynomial and evaluate at the inverse of the x value to find the y value. As you can see here, we implement the x value and take its, use this to isolate the y values, which then we solve for using the x values, and we get our error polynomial, which we then subtract from the received polynomial, and we receive the sent polynomial.